now. So this way it's easier to synchronize with the actual time. And we are going to get started now. All right, so I did not get the time that I thought I would have, to make a solution or make a presentation or pre-record a presentation about the exam. So I'm going to go over that today. Um, I learned a lot of stuff, making this exam. I actually learned about how to use cascading style sheet to keep things on one page, so it won't do a page break like between right inside the question, because that would be kind of suckish, because now half the question is on one page and the other half is on the other page, and you have to go back and forth just to read the entire thing. So anyway, it was kind of fun, working out all the technical details, because I have not needed to print anything for 2 years. So, and it's good and bad, because during the pandemic, I use Google Doc to collect the answers. So the good thing is, I don't have to walk around the classroom and staple stuff. I just basically go like, okay, this document is no longer shared. Done. You know. Um, Anyway, so question number 1, 2 are very similar in terms of the structure. You are given a particular set, in this case, in set C, and you need to answer the following questions. There are 5 parts to it. Okay, so this boils down to, do you understand the notation? That really is what it boils down to. And by design, I actually intended to test whether you understand the notations or not. So this notation here will focus on one thing at a time. So this notation here is basically saying there's a way, okay, to find the values of v, w, and x, they all being elements of C, such that x is v minus w. That's basically what the notation is trying to say. So what you need to know now, or what you need to do, is to take a look at the elements of C, and you ask yourselves, can I find values, put those into v, w, and x, such that one is the difference between the two others? I'm not giving you a whole lot, so I'm not giving you like 60 values and try to find the one that is the difference between the other two. So there are actually 2, if I remember correctly, because 5 minus 11 is -6. That's one. And I thought there was another one, but I could be wrong. Yeah.
-4 minus -6 equals 2.
There you go. Okay, -4 minus -2, -2 is -6. All right. So there are 2 examples. And that's what I'm expecting from the answer, because the question said, explain your answer using the meaning of the symbols. So I want people to say, okay, this symbol means there exists at least one, there's a way, that sort of stuff. And then to mention that, we are trying to find 3 elements, or potentially up to 3 elements in the set C, such that one is the difference between the other 2. So I'm looking for descriptions like that, and also to find the exact values. Like, if I make x equal to -6, and I make v equal to 5, and I make 11, equal to w, then this condition is true, and we only need to find one instance for this whole thing for one instance to be true, for the existential quantifier to be true. So you don't need to give me both of them. You just need to give me one of the two. So there was a question, during the test of, well, what if there are multiple ways to satisfy the requirement? Just give me one, because that's all I need. So what if people give me both? It's going to be okay too, not a problem. So that's part 1. And then part 2 is, once again, part of it has to do with the notation. So we are trying to define a set D such that an element R of D satisfies this requirement. R has to be an element of C. So right away, okay, and there's an and right after that. So right away we know that D is a subset of C, just like that, because everything in D also has to be in C. That is a requirement for something to be in D. But there's an extra requirement. The extra requirement is for all PQ in C, R does not equal to P minus Q. What is that saying? It's basically saying no matter how would you instantiate values for P and Q, being elements of C? You cannot find that R is the difference between P and Q. It is exactly the opposite of what was, in the first part of the question. So that will be the other three elements. So in this case, I'm looking for elements in C such that it is not the difference of any elements in C. So 2 is one of them, 5 is one of them, and then 11 is one of them. Negative,
Um, 5 minus negative 6 is equal to 11.
you're right. So 5 is, wait, okay, so
11
5,
is not 1, then 5 is.
5 is, yes. And I think 2 is 2, minus 4, minus negative 6, oh, that's 2.
Negative
So,
2.
so 2 is not one of them. Because negative 4 minus negative 6 is positive 2, so 2 is not in the set D. Is that okay? So how do you do this systematically? So if you want to do this systematically, you look at each one and say, oh, is that a candidate? Can it fit into the row of R? So you look at negative 4, and then you ask, is negative 4 minus 2? No. Is negative 4 minus 5? No. And so on. But I think since we only got like 5 values, it is relatively to go through every single one to find the answer for D. And then E is defined to be the difference or everything in C that is not in D, those elements would belong to E. So basically E is the same elements of E is going to meet the requirement of X in the first part of the question. Yep.
For number two, that question one, PQ can also be the same number, right?
PQ.
For all PQ,
Yes,
P and
PQ
Q
can be the same number. Yes. But the important part is no matter how you choose your P and Q, R cannot be the difference between P and Q.
But in general, that's what the notation means. You for all PQ, it can be the same number, right?
Yes, they can be the same. Yep. You basically have a double loop. You can see this as a double loop where P iterates through every single thing in C, and then so is Q. But one loop is nested within the other. All right. And then number 4 is what is the cardinality of the intersection? Just because of the way E is defined, what do you think is going to be the intersection between E and D? It's the empty set, exactly. Because by definition, because of the way we define E, even if you did not get the first or the second part right, you can still look at the third part, which defines what is E, and then you look at number 4, you can tell right away that the intersection has to be empty. Because by very definition, everything in C that is not in D is in E. So that means they cannot have any intersection, which also automatically answers the next question, which is the union between E and D is going to be the same cardinality as C, which is just 5. You just count it. So some of these questions or some parts of these questions do not really depend on the right answer of an earlier part. All right, so question 2 is about the same, except we are not looking at subtraction, we are looking at addition here. So that's the only difference. So in this case, we can see 11 plus 2 is 13, so that's 1. We can see that the sum of 2 and 11 is 13. So that means this existentially quantified statement is true because we find at least one way to find the values of V, W, and X such that they are all elements of M, and X is the sum of V and W. For number 2, we are looking for things that are not sums of any other two. So we look at 7, and I do not see a way to add up to 7 from the other elements. I look at 2, doesn't seem possible. Look at 11, doesn't seem possible. I look at 13, it is possible because 7 plus 6 is 13. 2 plus 11 is also 13. So there are two ways to satisfy that requirement. So 13 is not in the set. 6 is also in the set. So in this case, we have 7, 2, 11, and 6 being in the set. 13 is the only one that is not in the set of n. Is that okay? And then if you got the third part of the first question correct, you're going to get it right for the second question as well, because of the relationship between P and M and N. The subtraction here basically says P has all the elements that are in M but not in N. Same kind of scenario as before. And as a result, the intersection is going to be an empty set. As a result, the cardinality of the intersection is going to be 0. And then when we get to the last one, that looks like pun, but it's not. Well, I guess I can say no pun intended in this case. So anyway, the union is going to reconstitute M itself, which is the original set right here, and then the cardinality is going to be just 5. We okay so far with the first two questions. Okay, then we shall move on to the next three. I think they are very similar. The next three. All right, so we'll go to question number 3 first. So you are given that f0 colon a points to b. All right. So what is that notation? What is that telling you? What is it confirming?
F0 is a function.
Yep.
A is the domain, B is the code.
Exactly. So now we know f0 is a function. A is its domain, B is its codomain. Now, do we know exactly how elements are mapped? No, not at this point. We just know that it is a function. Similarly, we can now look at f1. F1 is also a function using B as a domain and C as a codomain. And then I proceeded to kind of spell out what is in A, what is in B, and what is in C, and also to further spell out what is F0 as a set and what is F1 as a set. So the first paragraph really just boils down to notations. Okay, do you remember what these notations, what they're representing? That's basically all that is. All right, so the second one, or the second paragraph, is just saying that when you apply a function, you can basically say f of x is y if and only if xy as a two-tuple is an element of f. In other words, I'm relating what you normally look at a function, from a math class, which is, we put the argument in parentheses, and then we say the result of applying the function is y. But in this class, we have a slightly different view. We can look at it as a two-tuple, where x is an element of the domain, y is an element of the codomain. And if this two-tuple is an element of f, then we also know that x from the domain is mapped to y in the codomain. So they mean exactly the same thing. And that's why there's an if and only if, which means if one side is false, the other side has to be false. But if one side is true, the other side also has to be true. Is that okay? Does anyone want to tell me why, in this specific case, I do not have to say x is coming from the domain and y is coming from the codomain? Because f is a function. Okay, so I already have that limitation applied, knowing that f is a function, because that's given here. F is a function. Is that okay? Does everybody understand what I said earlier? That I do not need the extra constraint to say that y has to come from the codomain and x has to come from the domain. Okay, all right. All right, so the actual question starts with the third paragraph, which says, now let's define f2 is a function. It maps from A to C. In other words, A is serving as the domain and C is serving as the codomain, such that f2 of x equals to f1 applied to f0 of x. This is basically a compound function. We are applying a function on top of another function. So are we good so far? I did not use the compound function notation, which looks like a tiny little circle between the two function symbols, which is, in a math class, that's what they would have used, is to use that symbol to mean, a compound function. But I chose not to do it. This is the more kind of spelled out, layman way of defining a compound function. Are we okay so far? All right. This can also be interpreted as blah blah blah. That's just the other way to say what a compound function is doing. But it's probably worthwhile to understand what that is saying. Okay. So for all xz is in f2 if and only if y for there exists a y in x there exists a y such that xy is in f0 and yz is in f1. In other words, y is a connector. It is connecting between x and z. X maps to z. This is the set that we are creating or that we are defining right now. But we are using the existing function f0 and the existing function f1 so that we are saying, if you can find some value y, so that x maps to y and then y maps to z, then x maps to z in the function that we're defining here. Are we good so far? Just several ways of defining the same thing. Yes? Okay, all right, good. So then the question has three parts. The first part is to express F2 as a set. Your answer should start with F2 equals 2. So in this case, after the equal to, I'm expecting braces, okay? Because it is a set. You need braces in order to specify where the set begins and where the set is ending. Inside the set, okay, I'm expecting two tuples because F2 is a function. Every function has two tuples as its elements. The first item of each two tuple comes from the domain, and then the second item of the two tuple comes from the codomain. So now the question is exactly what two tuples are we expecting here? I'm too short to point to the numbers, so I'm going to do it standing here. So we have 4 maps to C, and then we have C maps to R, so 4 maps to R. So 4R is one of the two tuples. 5 maps to E, E maps to N, so 5N is going to be another two tuple that we will find in F2. And then we have 1 maps to A maps to Q, so 1Q is going to be the third. Well, I shouldn't say third because that implies ordering is important, but that will be the remaining, two tuple in the set F2. Are we doing okay so far in terms of the explanation of part 1 of question number 3? Okay. Yep. Go ahead.
Did you randomize all the elements for
Yes.
each of our tests? Okay.
Yep. In my code, it's called scramble. So before I print it out into the test, everything is scrambled first.
So this is not identical to the test that we did,
Or
that I.
This test was never given to a student in the class.
Okay.
There were 24 students, and this is the 25th test.
Okay. That makes sense.
And I'm pretty sure no 2 students in the class got the same question either.
I was looking at it, I was like, ours might be different.
Nope, yours is definitely different in terms of exactly what is in the set, but in terms of the nature of the question, it will be identical. Yeah, I try to make sure all the tests, all the variations are the same difficulty. All right, so the second part of the question, that's a good question. So the second part of the question is, what is the value of P2 of F2AC? Okay, what is P2? Well, P2 is actually the same, it's defined exactly the same way as in the exam from spring 2022. That has not changed, okay? The font has changed a little bit because I changed the way I typeset, the whole thing, but it's still the same thing. So let's take a look at F2. F2 says, F2 of FDE is F1 of FDE. F1 of FDE is just confirming whether F is a function or not. Okay, so if you look at this whole thing here, that is just confirming that F is a function, that every element of the domain maps to one and only one element in the codomain. That's all it's trying to say. So, okay, in order to qualify for P2, F has to be a function first. Okay, and then we look at the second part of this. That should look familiar, okay, because it says for every W in the codomain E, W should be mapped to from something in the domain in F. And if you look at the cardinality of how many things map to W in the codomain, it should be less than or equal to 1. So all that is saying is you can only map to one thing in the codomain up to once from the domain. And that's another way to say it is injection. So P2 is basically saying it is injection. But you don't even have to take my words for it, right? Because it's kind of spelled out here. It says F D to E is injective but not surjective if and only if PI, that's just a new P predicate. But this is the important part. It is injection but not surjective. So P2 is true if and only if a function is injective, and then P3 is true if and only if a function is surjective. We good so far? All right. So now that we know what is P2, we get back to the question to answer the second part. This function is indeed surjective because everything in the domain maps to a unique element in the codomain. So it is injective. It is also surjective because every element in the codomain is mapped to. So if you look at the set C, which is N, Q, and R, they're all mapped to by elements in F2. So it'll be true and true, which means there's nothing else you have to say because the question clearly states that if the value is false, explain how the quantified statement is false using a concrete example. Since it's true, there's nothing else you have to do. Just tell me it is true and you're done with this. Are we good so far? All right. Well, since there are 3 questions of the same kind, so you would probably expect, certain things would not be the same, because otherwise it's not going to be. There's no point in doing it. All right, so we'll take a look at question number 4, and I'll just skip all the way to the set first. Okay, part 1 of the question. So we will take a look at how things are mapped. 2 is mapped to A, and then A is mapped to K. So we end up with 2K as an element of F2. Okay, so that's 1. And then we look at the second one, which is 3A. So 3 is mapped to A, and then A is still mapped to K. So 3K is another element in F2. And then we look at 1D is in F0, and then DN is in F1. So 1N is going to be also an element of F2. Are we good so far? How I worked out the 3 elements of F2? So now when you try to answer the question, it should be false in both cases. Yep.
If you don't mind, could you write F2 on the board so I could
Yeah, sure.
visually?
Yeah. Let me see how to do that. Because I need to, I cannot remember. And if I write it here without showing you, it's just going to be, okay, I think I got it. I think I can take a screenshot on one side and then write once I have the screenshot. So give me a second here to do a screenshot. Oh, no. My mouse button is a little flaky. Good thing I'm not playing, League of Legends. I did not intend to do that. It goes, I cannot play League of Legends, not with real people, just because of the pressure. It's like if I mess up anything,
It's over.
it's over,
They
man.
just treat you like trash.
Yeah,
What do
they're
you mean you play mid? What do you mean you play jungle?
they're really salty people around. All right, so let me paste that here. There we go. Oh, that works out okay. All right, so we are looking at the membership of F2. So and so we are looking at, okay, we'll just kind of go through elements of F0 first. So we can see how 2 maps to A, and then in return A maps to K. So 2K is in F2, so we have 2K. And then we look at 3a. A still maps to k, so 3k is also an element of F2. And then last, we look at 1d. D itself maps to n, so 1n is the last element in F2. So that's basically, so step one of the question is exactly the same as the previous one. But when you go to step two, it is false. Okay, this function is not injective. Why is it not injective? Because we have two elements of the domain, 2 and 3, mapped to the same element in the codomain. So the way you can answer that question is several ways. I mean, the format is not that important to me. So you can point out that K is mapped to twice. So when you look at the cardinality of the set in P2, it actually has a cardinality of 2, and 2 is not less than or equal to 1. And therefore, it fails the condition of the predicate P2. So that's one way to answer the question. You can also just explain and go like, well, since 2 maps to K and 3 maps to K, it is not a, 2 and 3 do not map to unique elements of the codomain, and therefore it is not injective. We can explain that way too. Is that okay? And then we look at part 3. So part 3 is asking whether it is surjective or not. The answer is it is not surjective. The best way to answer that question is to basically name an element in the codomain that is not mapped to at all. So in this case, the one that is not mapped to is R. Okay, so R is not mapped to at all because we can see how N is mapped to, K is mapped to, but R is not. So we can basically say the cardinality of the set in P3 has a cardinality of 0, and 0 is not at least 1, and therefore the condition is failed. Is that okay? All right. All right, so moving on to the last one, but the last one of this flavor. One of the reasons why I ask the same kind of question a few times is, just so that, if people were making some careless mistake in one, but did it correctly in the other two, then I know it is just a clerical mistake and not a conceptual mistake. All right, so this is the third one. So the third one, if you look at the mapping, do you want me to write it out? Nope. Okay. So in this case, we have 3 mapped to D, D maps to N. So 3N is in F2, 0 maps to E, and then E maps to M. So that means 0M is also in F2. And then 2 maps to B, B also maps to M. So that's why, 2M is also in F2. So even though the characteristic is reversed between F0 and F1, we still end up with F2 being not injective and also not surjective. Because we still end up mapping 2 elements in in A to 1 element in C and leaving 1 element in C not mapped to. Is that okay? I did not bother, I thought about it, but I did not. I thought about asking, whether F0 itself is bijection, injection, or surjection, and then do the same thing with F1. I thought about doing that to kind of add to the confusion, because you will find that in one question, F0 is not injective and not surjective, but then F1 is bijection, is bijective. And then the other one flips the role. But in the end, when you look at the compound function, it is neither. It is not injective and it's not surjective. So I thought about doing that, but then I thought maybe it would take up too much time, and so I did not do that. Are we good so far? All right. So we're moving on to the last one, question number 6. So question number 6 is is a way to encode a string into a single integer. In other words, the entire length of the string is the dimension, the dimensionality. Yep, there we go. So if you have a string of 5 characters, technically it has 6 dimensions, because the terminating null character is the sixth value. You're mapping your six values with six dimensions into one single natural number. Okay? So the way I do it is I specify that, so this is G, okay? G is like pretty standard. It is x plus y times x plus y plus 1 divided by 2 plus y. I think you guys should recognize it, and it's the same as the G function in the module itself. So G encode is the only new function here. Um, Nobody asked me about these interpretations, but that's good because the first thing is to ask is null. Is it null? Is P pointing to a null character? If so, just you return 0. Otherwise, you return G of um, whatever P is pointing to, and then you encode the rest of P, the rest of the string that P is pointing to. Is that okay? All right. So So what we know is if you have a multi-character string, okay, the best way to do this is to graphically illustrate it. All right, so the best way to illustrate this is let's just say that you have, we'll just call it x, y, z. Okay, so we have the value x, y, z, and then the null terminator. So these are the four values that we want to process using G encode. So now the question is, how are we nesting all those functions? So now you have to apply the actual function, the recursive function, and then you look at this and go like, let me switch back to the algorithm first, just to kind of take a look at it. So we are going to, the first character is going to be combined with the G encode of the rest. Okay, so getting back to my notation here. So we are basically saying, we have G of X combined with the G encode of the rest. So the G encode of the rest is going to be the G of Y, with G encode of the rest, and the G of the rest is going to be the G of Z, and then finally a 0, because the 0 just returns a 0. And then now you close all the parentheses. That becomes the value when we have a string that has exactly 3 characters, or unsigned 8-bit characters, followed by null terminator. This is what it boils down to. That's how the nesting is structured. Okay, so let me just pause here and see if there are any questions. Are there any questions relating this particular example that we have 3 values in a string, null terminated, and it translates to G encode is going to return exactly the value of the nested application of G.
Question.
Yep.
What portion of the code was recursive?
All right, so when you look at G encode, it calls itself. That's why it is recursive. Let me get the pointer. So this is the function G encode, and you can see in some cases G encode is going to call itself, and therefore it is recursive. So I'm relying on pointer arithmetics. In other words, if P is a pointer, then P plus 1 using pointer arithmetic is the address of whatever is next to the thing that P is pointing to. So there are a few ways to express this. I just chose not to use the array way of expressing things, just use the pointer way of expressing it. Is that okay? Do you guys know what I mean when I said, I could have expressed this using the array notation? Yes? No? Maybe? Did you guys learn all that stuff in CISP 360, 400, and hopefully eventually also 430?
You mean like brackets and then like
Yeah.
an iterate like an I or something?
Yep. Okay, let's go there because I really want to show you guys, alternative ways of expressing exactly the same thing in C and C++, even though this is not a C++ class. But I think, I would think people should have learned it, or I would think the professors would have taught it at this point of time. So let me just kind of do this part here. because I cannot remember, what I'm supposed to explain, so I need to do this trick all the time. Okay, and then we switch back to Zernal. There we go. Okay, so I can re-express. I'm just going to look at the expression itself, just to the alternative notation. So this thing here is really exactly the same thing as p bracket 0 equals to 0. Okay, so let me just kind of pause here, making sure that everybody understands that those two expressions are equivalent. It's just that one is looking at p as an array, and the other one is looking at p as a pointer. There is no difference, okay? In C and C++, there is no difference between a pointer versus an array. It's just a notation difference. So the negation symbol here, this is the logical not, right? So logical not is just negating whatever is next to it, which means when we get to the asterisk p, the compiler is forced to understand asterisk p should be interpreted as a Boolean. In C and C++, anything other than 0 is true. So that means in order for the negation of asterisk p to be true, p has to be pointing to something that is not null. That is no, sorry. Yeah, p has to be pointing to a null value. So that means it's exactly the same thing as the other way, which is looking at the first element of the array, quote unquote array, pointed to by p, and we want to confirm that it is null or 0. So now we look at some of the other stuff. So this thing here, okay, I think this part here should be pretty clear by now. Okay, and then the last one is p plus 1. So p plus 1, it is pointer arithmetic. It really boils down to something. If I were to express this using array, it's cumbersome because it's going to boil down to the address of p bracket 1. That's what it's going to boil down to. In other words, I look at an array and say, if I take away the first thing of that array, the rest of that thing is another array. And then I pass that along to the next invocation to do this whole thing again. Is that okay or not? I really should have kept people who did not take the prerequisite classes, because this test, this exam, would basically tell those people, it's like, I should have taken those classes or should have delayed taking your CISP440 until I have taken the other classes. Is that okay so far? All right, okay. So now let's get back to the question because I forgot about what the question was asking. So the question is giving you a natural number. Okay, so let me get my pointer back here. All right, so it is saying that assume that unsigned char nums64 is a null terminated array of 8-bit unsigned integers to be encoded. So I give you the characters to be encoded, and that G encoded nums returns a value of 93,955. So mine is a little bit large. I think some people got a smaller value. It doesn't really matter because in the end, you still need to use a specific way to kind of decode it. So the question is, what are the value of the elements in nums? In other words, given that this is the value. Okay, let me copy it. It's 93. Okay, I can just write down on this side. It's 93955. Okay, there we go. And okay, so this is the question. I know that g of x, comma, g of y, comma, g of z, comma, 0, close parentheses, equals to exactly 93,955. How do I figure out x, y, and z out of this? Yep.
You just doing the inverse function until you get 0.
You just do the inverse function. So the question is, what when you do the inverse function, you get two values, right? You get the x and the y. So the question is, when you get the x and the y, which one is which one? So the first time you apply g inverse to this value, the x is actually this x here. The so-called y is g of y of g of z 0. So what do? You apply the inverse function again. So the second time you apply the g inverse function, you end up knowing what y really is, and then it becomes the other value becomes the g of z0. Now you won't know it is g of 0. You will have to do the inverse function one more time, but then you will find that the y of applying the g inverse function ends up with a y value of 0. That's when you know, oh, we're done, because there's nothing else to decode except we also get z out of that whole thing. Okay, so let's go ahead and do this, okay? Because I do want to show you guys how that works. Do you guys want me to actually numerically go through this, or do you want me to just kind of symbolically show you how to resolve it? Let's do it.
Let's go.
Hmm?
Let's go.
Let's go. Yes. Okay, so that means I'm gonna have to look up the material because I cannot remember W of n, because the W of n is the magical function that can help us with the inverse function. So it is a good thing that this is an um, open book, open notes exam, because I would not be able to remember all those equations, even though I derived the equations. I would not I don't remember those equations. All right, so why is it taking so long? Come on, go. Uh-oh, this doesn't look good. The power server is busy. Uh-oh, uh-oh. Wait, I know how to get to that because all the content is on this computer too. I just uploaded to the server, for you guys, but it's actually all here as well. So let me get that from here. All right, so we want to get to. I just cannot remember what module we are talking about, but I can know which module because it says it's 0293. Okay, there we go. So DRTAK teaches modules 0293, and I need this file. There we go. Okay, so this is a local copy. I think the power server for some reason is not working anymore, at least for now. All right, so we can go to. Oh, there's something else is going on because I think the um, MathJax is not working either. But that's okay too, because you can see how all the equations are not they're not being rendered correctly. But this is all I need. I just need to get to this part here. And then I need to put it into a spreadsheet. A spreadsheet would be helpful. So let me go there. Look at Drive. Oh, I know what is going on. My Wi-Fi has gone bad. It just happens, kind of occasionally, like every class. But if I just kind of drop out of the connection and reconnect, it works like that. My recording is fine because I am using my local hard drive for the recording. So the recording is fine. There's no streaming anymore. It's just that at the end of the class, I have to upload a 1.7 gigabyte file. it's no big deal. The school is paying for the Wi-Fi and also the internet connection. All right, so let me just go to the share drive. So this way, as I work on it, you guys can see it. So we'll make a new spreadsheet. And I'm going to call this G decode. Okay. So I'm going to do it by hand first, and then at some point we can go ahead and do it by some other means. So we'll copy the value, which is the initial value is 93955. There we go. All right. So now we have to apply the inverse function, and the inverse function is documented here. And okay, now it renders just perfectly. So it's the floor of the square root of 8 times n plus 1, the whole thing minus 1, the whole thing divided by 2. Let's see how much of that I can remember. So I remember a floor. I remember a square root. And in the square root, we have 8 times whatever n is, which is this thing here. Um, and then I cannot remember. Plus 1. Okay, so the whole thing here plus 1. And then we take the square root, and then we subtract 1 before we divide the whole thing by 2. So we need to have another pair of parentheses here. The whole thing divided by 2. Close the floor. And now we have 432. But that's just Wn. Okay, let me give you the header too. So this way you can tell what is what. This is n. This is W of n. And so we need to look up x. X is Wn times Wn plus 3, the whole thing divided by 2, minus n. Okay, I don't think I can remember that much. We'll try. I will try. Well, the other way to do that is to peel this off and see if I can show both at the same time. And scroll that up. Oh, I cannot scroll up anymore. Okay, we can make that smaller. And then slightly bigger, like that. I only need to copy that once because I can replicate the equation afterwards. So now this is x of n. All right, so now I can actually say this is this number times this number plus 3, the whole thing divided by 2, minus n to begin with. That's my x. Looks kind of neat, right? And then the other one is n minus this number times this number plus 1, the whole thing divided by 2, 427. There we go. So now I can maximize this screen again because I got the equations in already. All right, so are we okay so far? Do you guys understand what I have just done? I start with an n, I apply the inverse function, I end up with the first value returned as a 2-tuple being 5. So that means the first element has a value of 5. So I get that much already. And then the second value of the first application of the inverse function gives me 427. What am I going to do with the 427? That's the end of the next iteration. So I now say, okay, let's make this value exactly the same as that one, because now I have just given myself another problem to solve, but it has the same nature, right? Because I have n, I need to reverse that back to the x and the y. And this time, I can just do this. This is why I like a spreadsheet. And then you look at 21 and go like, that's not 0, because we have to get to a 0 to know that we have hit the end of the string. So we have not done that yet. So now we have to say, let's try that one more time. Okay, this is the same as this value of 21, and reapply this. And this time we do get a 0. So the question is, what are the values in the array? What is in nums in this case? The first value is 5, the second value is 7, the third value is 6, the last value is 0. It's a null terminator. We good so far? All right. So I know this is a lot of math and stuff like that. So if you do not want to do this by hand, you can give me the algorithm to do it. Does that look like a loop to you? And if it does look like a loop, what are we doing per iteration? And how do we connect one iteration to the next iteration? And how do we get out of the loop? Those are the questions you should ask when you see something that seems to be repetitive. So what I'll do is I'm going to do this one more time and put a 0, just copy this value over here. So now, by the structure of this spreadsheet, what is demonstrating, how do you make a program to do the same thing? Well, first of all, we know it's a loop. You can do it recursively too, okay? But I would just kind of use a loop to do it. And the first thing you want to do inside the loop is to apply G inverse, which means you're going to have to define Wn. The question specifically said to not refer to a function as defined in the module, because I want to know that you know what Wn is. Okay, so all you have to do, if you want to go for the route when you give me the algorithm, you just have to say, okay, this is how I define Wn, and then just copy everything in from the module. So you apply Wn, and then you in return you compute the x and the y, and as long as the y is non-zero, you have to go for another iteration. So the y value of the prior iteration becomes the end of the next iteration. So you keep doing this, and you have to keep incrementing p so that it points to the next location. So you'll be populating the array that was initially pointed by p, the pointer. And then when you get to the null terminator, you still have to copy that one more time, okay? Because the null terminator is supposed to be a part of the array as well. Is that okay? All right. So do you guys want to see the code? Yep.
So before you did all this, how did you determine that nums had 4 elements to it?
Let me take a look at the question. I think that. Let me take a look. It may not be. You may not. I don't think it's given to you how many elements it has. So you basically have to keep going until the y value after the application of the inverse function is a 0.
Yeah, but before we did that, you
Mhm.
had already stated that you knew that there were.
Oh, I was
going to
using
be
an
4
example. I was just using x, y, z as an example.
Oh,
Yeah,
okay.
that turned out to be exactly the
Yeah.
same number
Oh,
of
okay.
values as the actual case.
Yeah.
But I was using it as an example to illustrate how the application of G is nested.
Okay.
Yeah, when you look at the array elements, the first element is G of the first element, and then comma, and then G of the second element, comma, G of the third element, and so on. So that's basically the pattern of how and it comes about. Mhm. And then that also gives you the clue that when you apply G inverse, the x of the first application of G inverse is going to be the first element. So you look at the second value of the application of G inverse, and what you do is you look at that and go like, oh, this is G of Y something. So you apply G inverse again. You just have to kind of repeat the application of G inverse until you get to a 0 as the Y value. That gives you the flag of we're done. Is that okay? Okay, how did you guys answer this question? Did you guys mention anything about the nesting, how it is nested? Because that's partial credit right there. I mean, if you understand how the value 95,955 is the result of applying G in a nested way and the structure of the nesting, if you can identify that, that is partial credit. Nope. Okay, maybe. Okay, I have not started to grade it yet, so I guess I'll see what kind of answer people turn in as I grade it. All right. So are there any other questions? Are there any questions about the first exam or exam one? So I do. Yeah, go ahead.
So you want to go with the code method, um, maybe because I'm using different language, I don't remember. Is the array of C and C++ expandable, or do we have to predefine the length? Because if not in this case, we have to deal with like a linked list of some sort.
Nope, nope, no, no. You don't have to deal with a linked list. So let me give you the code in C++, or at least something that resembles pseudocode, because I do want to show you that.
Yeah, it's been a bit since I used C++, so I don't remember how the array specifically works.
Okay, so we'll take a look at G decode, right? G decode starts with a unsigned char pointer to P, and then whatever value that we are given with, so that's going to be U in 64 underscore T, just to make sure that it's large enough that we can encode a relatively long string. Okay, so this is the prototype. I believe that's the prototype that I gave you. Yes, I did. So now the question is, how do we convert what we just talked about earlier into actual code here? So the first thing you might want to do is to define a W n, because that's going to be helpful. So you just basically have U in 64 underscore T, W of U in 64 underscore T, N. And this one is really just a, you can say return the math floor function of square root of 8 times n plus 1. And then we need nope, that whole thing minus 1. The whole thing divided by 2. And then now I need to match the parentheses. I think that is good. Um, I think you need a typecast operator here. I'm not 100% sure, but we'll put a typecast here just to make sure that the value is casted to an unsigned integer. So now that I have that, I can now decode one level. So I know I can figure out x and y. So I can figure out u and 64 underscore t x equals 2. Oh wait, u in 64 underscore t w, because I want to get wn first. So that's how I can get w, because otherwise I'll be calling w over and over again, which is totally not efficient. And at this point, we can say w times w plus 3, the whole thing divided by 2, minus n. That's our x. And then we have u in 64 underscore t, y equals 2, w times w plus 1, the whole thing divided by 2, minus n. Um, it's surprising that I actually remember from earlier. Anyway, okay, so once you have x and y, now you can decide what to do. So this is the way that I actually write programs, is I just get the values first. So I can say, if y is a 0, we're pretty much done. Okay, so I can now say if y equals to 0, and we are pretty much done. But we might want to stash it to wherever p is pointing to. There we go. So now the else is corresponding to what if y is not null. If y is not null, then p, whatever p is pointing to, should get the value of x. And now I'm left with a y that is non-zero. So what am I going to do with the y that is non-zero? Recursion. Okay, so I can go for G decode. This time is p plus 1 because I have just put a value into whatever p is pointing to. So it's going to be the next location that the recursive call needs to put something into. And then what we know as n in this iteration, um, what we know as y in this iteration is going to be the end of the next iteration. So I would kind of do it this way. Are we okay so far? Okay, let me ask you this. How many people think recursion is harder than iteration, like using regular loops? It all depends on how you look at it, okay? So the trick here is to look at this and say an array consists of the first element and a subarray, the rest of the remaining part of the array. So once you see an array like that, and then you also look at the way we apply the G function, which is also recursive, then the recursive solution actually makes more sense to me. Because to solve the original bigger problem, I break a tiny piece out of it, solve that piece, which is our x in this case, and then say, okay, I know where you're supposed to go. You're going to go to wherever p is pointing to. But then I have a leftover piece because y does not equal to 0 if I get to the else case. So the question is, what am I going to do with this? Okay, I'm left hanging the g value of something else. Well, let's do it again. So the new y value becomes the new n for the next iteration. I just have to make sure that p is also incremented so that I put that value into the next location. So in my mind, which may not be the same as how most people think about these things, is I actually see the recursive solution first before I see the iterative solution. I can convert this into a loop, but this is the first thing that I think of when I try to solve the problem. And no, I did not have this program memorized right before class. I just derived the program as we go. Yep.
Shouldn't y be assigned to p plus 1? And p should be equal to x.
No, it is x. Okay, let me go back to the spreadsheet because the spreadsheet shows that. Um, where's my spreadsheet?
Which variable of the GD code is it pointing to?
So you can see how the y value becomes the next n, how the y value becomes the next n. The x value is the actual value of the element at that particular position of what p points to. It is only when we get to 0. Okay, let's do that one more time and then it will be clear. Because if you decode 0, you get all zeros. So that's how we get these 4 things, and they become the values of the array. So the first element is 5, second element is 7, third element is 6, and then the last element, which is the no terminator, is a 0.
Well, yeah, but in the code,
Mm-hmm.
you assign it to p when y is equal to 0. Wouldn't that happen when you get x equal to 6 in your example?
Yeah, I'm just shortcutting it. So this is me just kind of shortcutting it because if I see that y is a, oh, you're right. Okay, so I terminated it one step too early. So I have to say, yep, you're right. Okay, yes, I did make that mistake. Um, okay, so that means asterisk p gets x is going to be done anyway, so I can move it outside of the conditional statement. And then the only thing the conditional statement has to do is to say if y does not equal to 0, then we go for the recursion. Like that. Ooh, that is so much cleaner. I like it. Nice. Is that what you're talking about?
Yeah.
Yep. Because y is, whether we have a terminator or not, so when y um, equals to 0, there's nothing for me to decode anymore. So I'm going to get a B out of my own test for this question. Because the structure is, for the most part, right, but not entirely. That's definitely not an A kind of answer. All right. Very good. Is this correlating with what you guys are learning or have learned from CISP430? A little bit? The recursive nature of things? Mm-hmm. Okay, very good. That is why it's a co-requisite, of this class, because, the two classes actually kind of go hand in hand. All right. Any other questions about exam 1? Okay, I do want to remind people because I can see a few people may have a concern. Yep, go ahead.
Are you able to put the exam 1 paper up now? Not the answer sheet, but just like the actual like exam again. Say if we just want to like shadow box it or something like that.
Okay, each person has a unique set of questions.
Oh.
So that's why I need you guys to kind of write your name on the exam question sheets itself. I can send it to you.
Yeah.
It's just gonna be I'm gonna have to write a script to do it. Because what I want to do is I want to write a script so I have all your WIDs and then I have and then I just have to say okay you got exam 2, you got exam 5, you got exam 6, so that way I put all the variations in the folder, run the script, and it will share the right exam with the right person. Hmm? Sorry?
That's gonna be a script with a VLOOKUP, basically.
I can do it in Google Script, GAS, GAS, Google App Script. Um, I used to do that, in the pandemic. So all the variations of the questions, each exam paper or document actually has the ID of the student,
Mm-hmm.
and then I have a way to distribute all of that, and
Okay.
yep. So
That'd be fun. I actually wanna. Yeah.
yep.
Nice.
It's probably faster for me to do it by hand, but I want a systematic solution.
Yeah, you gotta. It's not about doing it fast. It's about doing it so you don't need to do it anymore.
Yep. Okay. So I'll keep that in mind. All right. So any other questions? Oh, right. I distracted myself. So one more important thing that I need to tell people, there are two things. One is what if the best score of this entire class is a 3 out of 4, which is a B, right? So typically, unless I have very strong evidence that the entire class really is up to just a B by my standard, otherwise, I will use a floating scale. So that means, the highest score, usually not the highest score, I'm gonna pick the third highest score as 100% and then scale everybody up. Okay? Now, that is good for people who are close to the highest score. Like if you have the second highest score, you also get a pretty good boost, okay? But it doesn't help people with a very low score because it's proportional. So people with a very low score to begin with, it's just a percentage increase, of the low score. So sometimes, I cannot guarantee, but sometimes I would also take the square root of the score and then multiply that by the square root of the actual exam score and multiply that by the square root of 4. So that way the adjustment is not linear. People with a lower score would actually get to see a larger percentage of increase, but yet it will maintain the order. Remember partial ordering and total ordering and stuff like that? It would actually maintain the ordering. So someone who started off with a better score than somebody else will still end up with a better score than the other person. It's just the difference may change. It still won't help people getting a 0. But it will help people getting a relatively low score. So I just wanted to point that out first, okay, before people get too despair over this. And then the third thing is I also want to remind people that my grading scale or the way I assign letter grades is linear. So it's 0%, 25%, 50%, 75%, and 100%. So an A is 87.5% or better. This is a B. So a B is starting at 62.5%. And then the C is starting at 37.5%. And a D is starting from 12.5%. And anyone who's getting less than 12.5% is equivalent to a letter grade of F. So I want to point that out first before people start to panic, because when the points are starting to roll in, people go like, oh no, I'm failing the class. I'm getting 7% of 100%. No, you're doing fine. You're getting a B out of the class. So just want to make that obvious first. All right. So are we okay now with exam one? Okay. Then we're gonna move on to and finish up. Yeah, we got enough time, I think. We can finish up the entire discussion of. Nope, this is the wrong spreadsheet, I think. Okay, I can close that. And you can always look at the spreadsheet after class because it is just a spreadsheet and it's already in the Google Drive. All right, so I'm just trying to find my the correct browser. There we go. Okay. So where are we? There we go. Right. So we were talking about relations, remember? And I think most people remember the beer commercial. And that's the discussion of the beer commercial. So that is the problem of partial ordering. So when you have partial ordering, it means you know for certain elements of a set how they relate to each other, but that you cannot relate everything. So if I just pick two elements from the set and ask, does this relate to this or the other way around, you may not be able to answer that question. So the beer commercial is really just an example of, there's no comparison between smooth but not rich versus rich but not smooth. Okay, so there's no comparison between those two. Which one is better? We know that rich and smooth at the same time is good, better than the other two. We also know that not smooth and not rich is worse than the other two. But between those two in between, we have no idea of how they order. So that's the problem with partial ordering. So in order for something to be totally ordered, you need to add one more thing. So the one more thing on top of the three qualifications of partial ordering. So in order to be partially ordered, you need reflexive, antisymmetric, and transitive. Just those three. But if you have the fourth one, which is called comparable, there are other names for that too, but I'll just use comparable. That will basically make the relation R a total order. Okay, so the next question is, what does it mean, when you say comparable? So comparable, which also has some other words for that, is basically defined by this quantified expression. It's basically saying no matter which two elements you choose from X, they can be the same. Okay, so I'm just choosing one value for E, one value for F, such that they are both elements of X. One of these two has to hold. Okay, E has to relate to F, or F has to relate to E. Is that okay? And that's the only addition. That's the only addition to partial ordering to make something a total order. So as it turns out, what we understand as less than or equal to is total order. So when when you think about how you compare integers, less than or equal to as a relation, that is totally ordered. So let's double check whether that makes sense or not. Okay, we're just going to do it in an intuitive way. Is less than or equal to reflexive. In other words, if I pick any integer, is it less than or equal to itself? Okay, that seems reasonable. Is it antisymmetric? In other words, if I can say A is less than or equal to B and B is less than or equal to A, if both of those are true at the same time, does that guarantee that A and B are the same?
Yes.
Okay, so that seems to meet the requirement of antisymmetric. Let's look at transitive. If I say A is less than or equal to B, and B is less than or equal to C, does that imply A is less than or equal to C? Seems to make sense, right? So it intuitively meets the first three requirements. And then the last requirement is, no matter how I choose integers, E and F, can I guarantee that one is less than or equal to the other one? I think so, right? If you look at all the integers, if I choose exactly the same number, the equal part is going to catch that, right? But if they're not the same, then one has to be less than the other one. So that means less than or equal to for numbers would meet all four requirements, and therefore it is, the relation itself, less than or equal to, is a total order. That's it. That's the part where we finish up the relations, topic. And some of you caught earlier that we also have a assignment. So the assignment is already released for relations, and this time you have two trials. So I just want to make it clear, the relation homework assignment is due on the 3rd, which is next Monday. You can still ask questions, over the weekend. I mean, even though I said, the turnaround time is 48 hours, usually it is less, okay? So you can still ask questions, and this one is really testing whether you understand the concepts of relations or not. And you do have two trials. So that's that. We are not quite out of time yet, okay? So I'm going to utilize the last 5 minutes to kind of point out what we are going to talk about next. In other words, what you'll be reading over the weekend, hopefully. It is called propositional logic. It is a interesting topic, I would say, because if you look up propositional logic in Wikipedia, it will give you some content that has a little bit of what I'm going to talk about here, but for the most part, it's not the same. That is because Wikipedia and most textbooks will talk about propositional logic from a human perspective. In other words, how do we use logic to argue about something? Okay, so you can probably get some of the overlap content from one of the philosophy classes, like critical thinking, may actually give you some of the stuff that is already here. But my perspective is from the computer science perspective. In other words, if I need to prove a theorem, okay, how would I do that? So the difference is, if you look at it from the human perspective, it is almost like trying to find a needle in a haystack. You guys go like, yeah, but everything that you teach, Tag, is like finding a needle in a haystack. Well, but this is different, okay? Because when you try to prove a theorem using propositional logic, you're trying to find a needle in an infinitely large haystack. So when do you stop? When do you come back to me and say, Tag, I don't think the needle is actually in the haystack? You cannot, right? Because the haystack is infinitely large. So no matter what you do, you cannot confirm that the needle is not in the haystack. You can only confirm that you have not found it so far. Is that okay? Mm-hmm. But the way I look at propositional logic, using these other additional concepts, one is called resolution, one is called CNF or conjunctive normal form. By combining these two, I make two claims. One is whatever you can express in Boolean as a Boolean expression, I can turn that into a CNF, a conjunctive normal form, which is kind of a strange claim, okay? Because I'm saying if you can use implications, if and only if, and or in any way that is properly structured, I can turn that into a conjunctive normal form, which essentially is a conjunction of disjunctions. Okay, that's one claim. The second claim is once I convert everything into CNF, the problem of trying to find that needle in the infinitely large haystack is not quite as bad anymore. The haystack is large, but it's not infinite. It has a finite space. Okay, it's finite. So you can basically go like, oh, I just need to set up like a loop inside a loop, inside a loop, inside a loop, but it's going to terminate. If the needle is not in the haystack, you can come back to me and say, I have searched everywhere in the haystack and the needle is not there. So that is the difference. But it is a shift of perspective of how we look at propositional logic, how we apply logic to prove theorems. So just want to give you that warning because if you try to read any other literature on propositional logic, it will be from the human perspective of how we apply logic. This starts off with that, but then it shifts to the mechanical aspect of using CNF. We convert everything into CNF, and then we use resolution and also proof by contradiction so that we have a finite haystack, and it's easier to answer the question of, is that needle in the haystack? All right, so I just want to give you that kind of overview of what this module is about so that when you read it, you don't get too lost in the details because there is a lot of details as well. Are we okay? All right, have a nice weekend. I will see you guys on Monday. So you got the homework and also a little bit of reading to do. And then on Monday, we'll start on this new module.